Let's look at how cements can be classified. They sometimes are used in different applications. I already told you the example of using cement in a column in a high-rise building versus using the same cement in a dam. You need different characteristics for the applications. Because of that, you sometimes have to define cement of different types which can be employed for specific applications. So cement can be classified based on differences in the chemical composition, differences in physical properties. For example, some cements are much finer than the others, okay? Differences in terms of sometimes putting extra additives into the cement powder, or sometimes you may have very special purpose cements which are not used for general purpose construction. So let me give you examples of different types of cements here. I am going with this universally applied classification called ASTM, or American Society for Testing and Materials. Okay, American Society for Testing and Materials, ASTM, basically brings out standards on all kinds of materials and processes and test methods and so on. So the ASTM classification for cement is included in ASTM C150. Okay. According to this, cement is classified as general purpose, type 1 cement, moderately sulfate resistant and moderate heat of hydration, type 2 cement, high early strength cement, which is type 3 cement, low heat of hydration cement, that is type 4 cement, and sulfate resistant cement, that is type 5 cement. And sometimes you add what is called an air entraining agent to type 1 and type 2 cements to call it type 1A and type 2A. I am not going to confuse you with all these cements, but let me just get to the basic understanding of what could be the differential components that are present in these cements. So of course, type 1 is a general purpose cement, that is cement that is available for use everywhere. Okay. You can take this sort of a formulation and make adjustments to get the other type of cements. So let's take two examples. Let's take high early strength. Okay. So what are the ways in which you can increase the early strength of the cement? We already talked about two possible ways. One is increasing the C3S content, increase C3S content, right? As I told you, C3S is responsible for early strength. The more the C3S, the greater will be the early strength. Okay. So where do you need high early strength cement? Supposing you want to very quickly build something, you can use high early strength cement. Supposing you want to build in a cold weather, where because of the external temperature you may start freezing the water in the concrete, you want high early strength cement to gain strength much faster so that it does not start freezing. Okay. So in such applications you want high early strength cement. So increasing C3S will lead to high early strength. You could also increase the fineness of the cement. Increase the fineness. So grind it much finer, that will make it more reactive and increase the rate of strength gain. So increase C3S, increase fineness to get high early strength cement. What about low heat of hydration cement? We talked about the different cementitious compounds, right? And the one which had low heat of hydration was C2S. Okay. So C2S has low heat of hydration. So in a low heat of hydration cement, you will have more C2S as compared to general purpose cement. Okay, so this is how you actually look at producing different characteristics from the same set of compounds, right? So this is overall the typical composition that is given by ASTM for the 5 different types of cement. So as I said, I was comparing high early strength cement type 3 with the general purpose cement type 1. So instead of 45 to 55 C3S, you have 50 to 65 in type 3. So you have more C3S. You may also want to increase your C3A, okay, because that's also responsible for early strengthening. Okay. What about type 4? You see that your C2S was 20 to 30% in type 1, but in type 4, that is low heat cement, you have 40 to 50% C2S. Okay. And you are reducing the components that produce high heat like C3S or C3A. Okay. So all these characteristics you need to keep in mind while thinking about how alternative or different cements are designed. So in relation to type 1 cement, that is general purpose cement, type 2 will have marginally lower C3S and C3A, type 3 will have marginally higher C3S and as I said, a higher fineness. Okay. Type 4 will have a lower C3S and also lower C3A content and generally much higher C2S content. Type 5 will have a lower C3A content. That is what you see in this table here in terms of the quantities of the compounds presented in different types of cements. This is just some examples of how these cements are affecting concrete properties from a textbook by Mehta and Montero. So, you see here what is plotted on the y-axis is the heat of hydration. That means how much heat is getting involved in the calories per gram, okay, versus age. So, the type 1 cement or general purpose cement is here. So, it evolves quite rapidly in the beginning and then it slows down. The rate of heat evolution slows down later, okay, and stabilizes. Type 3 cement, that is the high early strength cement, is liberating a lot of heat in the beginning and then it slows down, okay. That means it's reacting much faster. Type 2 cement, which is lower heat of hydration as compared to type 1, starts off slowly and then continues to go as long as hydration happens. So, please remember, as long as cement is reacting with water, heat will continue to get liberated. But since bulk of the cement is already reacted at later ages, the rate of heat evolution will come down, okay. With respect to strength development, if this is type 1 cement, it starts rapidly in the beginning, but then it slows down towards the end. If you compare type 3 cement, which is high early strength cement, in the initial stages you have much more rapid strength development, but then in the long term you may actually end up lower than type 1 cement. If you look at type 2 or type 4 cement, which are low heat, they will start off very low, but they will continue to gain strength and may at some stage even overtake type 1 cement. So, in other words, if you allow the cement to continuously react with water, in the long term it may end up producing a structure that is stronger than your general purpose cement with type 1, okay. But please remember, all this is dependent on a continuous supply of water to the cement. If water stops and cement does not have access to water, its reaction also will stop, okay. So, whatever water is inside the concrete, as long as it is available for reaction, the reaction will continue and the cement will continue to hydrate. But if there is no water, reaction will stop. Now, in some cases we blend certain components to enhance the properties of the cement or sometimes even just to lower the cost, okay. So, there are different types of blended cements that are permissible as per the ASTM standards. One is called Portland blast furnace slag cement, which is called type 1S, and the slag is nearly 25 to 70% by mass in this cement. Now, what is this blast furnace slag? You have learnt about the blast furnace process in the manufacture of steel. In your school, you may have had some lessons in which you say that the iron ore, right, it is put in this blast furnace along with limestone and carbon or coke. Limestone is used as a flux. It lowers the temperature at which your reduction of the iron ore happens to form iron, okay. Now, what happens with is this limestone basically has calcium oxide in it, and your iron ore will have a lot of impurities in the form of silica, alumina and some additional iron oxide that is present. So, what will happen is this slag which comes out as an impurity from the blast furnace process ends up having a nice composition of calcium oxide, silicon dioxide and aluminum oxide and sometimes even iron oxide, right. So, it is almost similar to cement, the slag that comes out, okay. The molten slag that floats on top of the pig iron in the blast furnace process can be used as a cementing material. So, it is rapidly cooled or quenched, solidified, broken into a powder and then used as a cement replacement. So, that is what is used in a Portland blast furnace slag cement, which is called type 1S cement, and slag content is typically 25 to 70% by mass. You can also have what is called a Portland pozzolan cement, in which case we use a smaller replacement of 15 to 40% of the cement by a pozzolan. A pozzolan is nothing but reactive silica. So, this combines with the calcium hydroxide that forms from the reaction of cement hydration to produce more CSH. Okay, that's what the pozzolan does. It basically combines with the calcium oxide to produce more CSH. And this reaction is obviously called the pozzolanic reaction. And as I said, as you form more and more solid products, it will start filling up porosity. So the pores will get more refined. As a result, your concrete will be more durable. So when you replace your Portland cement with blended cement, you end up with more durable concrete. Please remember that. Okay, you increase the durability when you change from OPC to other forms of cement. Again, just to reiterate, the pozzolanic reaction is the reaction between calcium hydroxide that forms from cement hydration and reactive silica that you get from the pozzolanic material to produce additional calcium silicate hydrate. So what you are doing is you are consuming this lime, okay, you are refining your porosity, okay, and you are also refining the interfaces. So if you consider aggregates, right, the cement paste around the aggregate is getting a lot more denser in the case of a pozzolanic reaction. Okay. This reaction is slow, so basically it leads to an overall reduction in the heat of hydration. So when cement is replaced by fly ash or slag, the heat of hydration reduces. So what happens is, instead of using a low heat cement for certain applications like a dam for instance, I can still use a general purpose cement, type 1 cement, but replace partly with fly ash or slag. That will bring down the extent of heat. This reaction is much slower than the reaction of cement hydration. Okay? But one way in which it gets accelerated is by the presence of alkalis and gypsum. Interestingly, both alkalis and gypsum are contributed from cement. We saw earlier in the structure of cement there are oxides like alkali oxides, sodium and potassium oxide, and of course we add gypsum in the final stages of cement manufacture. So all these components are still present to accelerate the reaction of the pozzolanic material. But nevertheless, the reaction of the pozzolan is much slower as compared to cement, which leads to a much better durability in the long term, at the same time reduces the heat of hydration in the early stages. Again, this is just showing you the heat of hydration in calories per gram with respect to the pozzolan content in the cement. At 7 days, it is coming down a little bit. At 90 days, the extent of reduction of heat of hydration is significant. Okay. Now, in certain cases where you have problems of undue expansions of the concrete, the use of pozzolanic materials brings down the expansion and reduces the tendency for cracking. Okay. So, overall today increasingly we have to prepare concrete with cementitious additives which are pozzolanic in nature to ensure that we produce concrete of a much better long term durability. Now, if you look at the Indian standard classifications which are covered essentially in this IS 269 for ordinary Portland cement. So, if you look at ordinary Portland cement in India, we define it into 3 grades, 33, 43 and 53 grade. And the grade of the cement corresponds to the strength achieved by the cement mortar at 28 days. Strength achieved by cement mortar at 28 days. So, I said earlier the compressive strength of cement is determined on the mortar. So, the grade of 33, 43 and 53 basically are referring to the strength attained by the cement paste, strength attained by the cement mortar, which is as per a certain formulation. Okay, that I should also tell you that the tests for cement are covered in IS 4031 and IS 4032. Okay, one is related to physical properties involving specific gravity, fineness, compressive strength, etc. The other is chemical properties, how to determine the oxide compositions and so on. Okay. So, 33, 43 and 53 grades refer to the strength in megapascal. The grade implies the strength in megapascal achieved by the cement mortar at 28 days. Now this 28 is quite funny because you will see this coming later in concrete design also. We always design for what is the 28-day strength. Okay. Now 28 days is taken as the definition of the characteristic time for the strength of the concrete. Okay. When you design concrete of a particular strength for a construction project, what you will also do is prepare some cubes and measure the strength at 28 days on those cubes to ascertain whether the concrete in the structure has met the demands of what is required. So this 28 days is a very sacred number. Okay. So couple of questions for you to understand why 28 days, why we consider 28 days strength. It is because most of the cement that is likely to hydrate would complete its hydration within 28 days for a general purpose cement when you are dealing with type 1 cement or a general purpose cement. Okay. If you think about low heat cement, 28 days is probably not enough to think about. You may have to think about much longer time period. So increase the time over which the reaction actually happens with water. Okay. So very often in construction sites, we are interested in finding out the 28-day strength. When we design concrete also in the laboratory, we talk about 28-day strength. Very often we also look at early age strengths at 7 days and 3 days depending upon what our requirements are. Okay. But here if you look at the grades of cement, they would have specified strengths at 3 days, 7 days and 28 days. The cement which is tested as per that standard has to meet strength requirements at 3 days, 7 days and 28 days. Okay. Now of course similar to ASTM standards, IS also describes low heat cement, rapid hardening or high early strength cement. It also calls Portland porcelain cement or PPC or Portland slag cement, which is otherwise known as PSC. Okay. In India, very often when you go to the market, you will talk about OPC, PPC and PSC. OPC itself, mostly what you will get in the market will be 43 grade or 53 grade. These days you do not get the lower grade cement in the market, you only get 43 or 53 grade cement in the market. There are no grades defined for PPC and PSC. Okay. You will only get one type of PPC or PSC. Of course, you get many different brands of cement. In India, there is no dearth of brands. There are so many different cement manufacturers. You get all kinds of brands of cement. So how do you make sure the cement is good for construction? Again, take the cement, do the analysis, determine the chemical composition, do the physical properties, do those basic tests that I talked about previously and ensure that everything is matching the requirements given in these standards. Okay. Whatever cement you buy in the market, as long as it meets these standards, it is fit to be used in concrete. Now, there are certain cements which are not belonging to the same category that we just talked about from the basic composition of the 4 different compounds that you have. These are cements which are produced in a slightly different manner. So one such cement is called expansive cement. Now, one of the common problems with concrete is its tendency to shrink. Right? We mix cement with water, some water goes into the reaction with cement, there is some water which is free. And slowly this free water will start drying out of the concrete. In other words, because of the removal of water from the concrete, the structure of the cement will change and there will be a slow reduction in the volume or contraction of the volume, which we otherwise call as shrinkage of the concrete. Okay, we call that as shrinkage. Now, if this shrinkage happens freely, there is no stress generated in the concrete. However, if this shrinkage is prevented from happening, then it starts formation of cracks in the concrete. Okay. So we want to avoid excessive shrinkage so that concrete does not crack. So in such cases, we use these special cements called expansive cements. What would happen is, in normal case, a typical cement paste would shrink with respect to time, right? Whereas an expansive paste will first expand when it's hydrating and then it will slowly shrink just like normal cement paste. But what is happening as a result? Your net shrinkage is being brought down significantly. The net shrinkage is being reduced significantly. That means the stresses that will be caused because of shrinkage will be reduced in an expansive cement paste. Okay, for several applications we use expansive cement to produce a net zero shrinkage or sometimes even a net expansion in the concrete sometimes. Okay, these are produced by adding special compounds to the cement. Okay, they are not regular cement, but they are produced specially. Not all cement plants will produce all types of cements or all special purpose cements. Okay, only some types of cement plants will actually produce all these special cements. There is also a cement called calcium aluminate cement, where the raw materials are not calcium carbonate, limestone and clay, but limestone and bauxite, that is aluminum oxide. Okay, so these produce compounds that are rich in calcium oxide and aluminum oxide or calcium aluminate. These are also called high alumina cement. Okay, calcium aluminate cements are also called high alumina cement. Now this type of cement became very popular after the end of the Second World War, especially in Germany, where they wanted to rebuild their infrastructure which had been completely bombarded and destroyed because of the war, right? So they started building rapidly because this cement gains strength very rapidly. As you can see from this picture of strength versus age, the high alumina cement gains strength much more rapidly as compared to rapid hardening cement or OPC. Right? So they started developing a lot of structures with high alumina cement which gained strength rapidly. Problem was, as this concrete made with this cement was exposed to the external environment with moderately high temperatures and humidity, what happened was the strength basically dropped over time. Okay, this happens because of an internal chemical compound composition which is changing as it is subjected to a continuous exposure to temperature and humidity. And because of that, you have a problem of using the cement for normal construction. Many of these structures that were built after the war had to be removed or destroyed because the concrete started reducing in strength, and as a result you had a lot of failures in these structures. Okay, so that happens primarily because of gradual conversion of the products of hydration. I am not going deep into the chemistry here. The idea is to simply tell you that high alumina cement is not good for general purpose construction. However, it is a very good concrete to use at very high temperatures, especially inside kilns, for instance, right? Inside a kiln where the temperature is 1000 degrees and more, the high alumina cement forms a nice ceramic bond, and because of which you will actually get an excellent material that is resistant to heat. There are other special cements also which are used for very specific purposes, like rapid hardening cement. Okay, rapid hardening cement is generally consisting of some amount of plaster of Paris, which is calcium sulfate hemihydrate, CaSO4 half H2O, or sometimes it may have Portland cement plus calcium aluminate cement, so that as soon as you mix with water, within a small period of time, let's say as low as 10 minutes, you get a rapid stiffening. So for example, you want to plug a hole in a water tank, for instance, you could use something like a rapid setting cement. It is not rapid hardening cement. We talked earlier about rapid hardening cement or high early strength cement. Those cements are formulated to develop strength at an early age, but they are not necessarily rapid setting. They set normally, but they can get strength at an early age. Here we are talking about rapid setting. Okay. Then you have white cement. Very often you see this ad on your televisions, right? That you use white cement to make these putties, right? White cement basically is used for decorative purposes or for lining between the tiles, right? When you joint the tiles, you'll often see it's filled up with white cement paste because there a grey will not be appearing very nice. So white cement is used for very specific purposes. So as the color is white, you can imagine that it's got very little iron content. Almost zero iron content is available. Okay, low iron content. And the advantage with the white cement is you can pigment it to color in any, you can pigment it to make it any color. Okay. Then there are other special cements like oil well cements which are used for oil well drilling applications. So when you drill very long bores into the rock to extract oil, to prevent the soil from collapsing, you need to line up the walls of the bore that you have dug with cement. And the cement should be such that it can flow very long distances after mixing, but at the same time when it comes to rest, it should be forming that layer on the soil surface so that the soil does not cave in. So it's a very uniquely formulated cement and it needs to have a combination of different types of additives to ensure that it is flowable for a long time, but when it comes to rest, it sets and hardens almost immediately. So again, this is something that needs to be formulated very carefully. Sometimes you may also, in some markets, have special purpose cements for masonry applications, okay, where we don't want to use lime, we don't want to use normal cement because it produces very high heats of hydration and can cause cracking of your plaster, for instance. You can use what is called masonry cement, and this is a mixture of cement, gypsum and limestone, or sometimes other fillers and also some air entraining agents, which causes a very nice consistency and ease of application as opposed to normal cement. Okay. Of course, it does not have as good a strength as your normal masonry cement, as your normal Portland cement, but at the same time, it is much better suited for applications for masonry purposes. Another special cement is called super sulphurate cement, which is based on blast furnace slag. You have a large quantity of blast furnace slag and don't have much cement clinker in the composition. And it is used for good resistance to chemical attack, which are otherwise quite dangerous for normal Portland cement like sulphate attack. Super sulphurate cements are good there. Problem is, in the long term, you have a slow reduction in strength. And that is why, again, super sulphurate cements are not typically used for general purpose construction. In fact, they are not really manufactured also to a large extent around the world. I was talking previously about tests on cement. I am just showing you the same here. The normal consistency and the setting time are done with the YCAT apparatus, which is shown here. The YCAT apparatus is shown on the right side here of the picture. So you have a mold into which you mix your cement paste and put it inside. Then you have a plunger, okay, a plunger of 1 centimeter, which is made to rest on the top of the cement paste and then dropped, and this plunger basically plunges into the cement paste, okay. And when it is at a certain distance from the bottom, if it stops, it's called normal consistency. That 1 centimeter plunger is used for determining the normal consistency. The normal consistency is nothing but the water content at the point at which the plunger just comes to a rest about 5 millimeters above the bottom of this mold here, okay. Now the initial setting, for the initial setting, we use a 1 millimeter needle. We use a penetrating needle which is 1 millimeter in diameter. For consistency, we use a plunger of 1 centimeter. For setting time, we use 1 millimeter, okay. And this 1 millimeter needle basically penetrates the cement paste up to a distance of 5 to 7 millimeters from the bottom. That's called initial set. And the point at which it does not penetrate the top at all, that's called final set, okay. The soundness is measured typically with the help of this Le Chatelier's mold. So the freshly mixed cement paste is packed into this mold, and you can put it in a special chamber where it is subjected to temperature and pressure to accelerate the reaction. At the end of one day, you see how much expansion or how much opening of this mold has actually happened, okay. So that's called soundness. Fineness is measured in terms of air permeability test. So this is the air permeability instrument, which is also called the Blaine apparatus. So here what we do is we pack the cement, okay. Cement is packed into a bed here, and what we are simply trying to do is, by application of pressure, we are trying to make air pass through the cement, make air pass through cement bed. So if the cement is very fine, what will happen is the gaps between it will be small. So the velocity of air passing through the cement bed will be much lower, it will be passing very slowly. If the cement is coarse, that means not fine, it will have large gaps in it, so the air will pass much faster. So based upon the speed of flow of air, which is determined with this U-tube or a manometer, right, you can then determine the relative fineness. So for that, you need to have the fineness of a standard material like a standard cement known, and this standard cement is available from the National Cement Based Materials, the Center for National Cement Based Materials, okay. Then you have the test for specific gravity. Sometimes fineness is also exhibited in terms of the amount of material that passes through a 90 micron sieve. So just take a sieve of 90 microns, put your cement through, and amount of material that is passing 90 micron sieve or retained on 90 micron sieve can be also used as a measure of the fineness. The specific gravity can be determined by a pycnometer method, by using what is called this Le Chatelier flask. Okay, this is a very simple test. All you're doing is putting your powder here and filling it up with a liquid like oil or kerosene up to a certain point, and then you do the same test without the powder and fill it up, and then by measurement of masses you can then determine, or measurement of the mass of the material added, you can then determine the specific gravity. Then you have compressive strength, as I said, on mortar. So these tests are covered in IS 4032, whereas the chemical composition tests for cement are covered in IS 4031. Now, it's very important that while this course is going on, all of you get access to the different Indian standards, whatever I have been mentioning in my lectures. We talked about brick and stone standard, concrete block standards, then we are talking primarily about the types of cement, standards for that, and then testing of cement. All these standards, it will be good if you go through these and then get yourself familiar with the kind of approaches that are there in these standard test methods. Okay, so we'll stop with this for today.